All right, after talking about series circuits, the next circuit that you would have explored in grade 10 in middle school is a parallel circuit where you have one battery that's operating multiple circuits from it. And so basically one way you can look at it is that these are actually separate circuits. They're separate, but they're running from the same battery at the same time. Okay, so they're running in parallel. And it looks like just like a daisy chain where I continue having these daisy bead chains with extra circuits attached to that battery. So how do they work? And one thing that we would have noticed is that if we keep adding another branch, all of a sudden these light bulbs become brighter and brighter, which is strange. It's different than a series circuit, that the more light bulbs you put in a series circuit, they become dimmer. But with a parallel circuit, for some reason, they get brighter. And that means that the current in that entire circuit starts to go up and up and up the more branches that we put in. So why does that happen? Okay, well, let's try to learn that by understanding how to apply Kirchhoff's current law in that circuit and learning how to calculate the total resistance so we can figure out why the current goes up when we add more branches. And then I'm going to teach you how to calculate the power going through each individual branch in a circuit. So what is Kirchhoff's current law of junctions? Well, as I just said above, okay, when we look at this, you treat this as two separate circuits. Okay, so I have a circuit running through here. Let's call that loop 1. And then I have a different circuit going through there, which I'll call loop 2. And they're connected. They're operating at the same time from that battery. And what ends up happening is those two loops meet at a junction, okay? As the current flows here, it ends up here. And as the current flows down here, it ends up here. And that red dot that I created here is called a junction. And the currents are going to add up. And if I had an ammeter in here, the ammeter would register the current flowing through the first loop plus the current flowing through the second loop. And that's essentially what Kirchhoff's current law of junction says. Kirchhoff's current law of junction says that the sum of the current going through to a junction is equal to the sum of the individual currents coming in. So I can call this current 1 going through that branch, and I can call this current 2 going to that branch. So at that junction out, the total current, I total, is going to be equal to I1 plus I2. And that's essentially what Kirchhoff's junction rule is. The total current inside of a circuit is going to be equal to the sum of the individual currents in each circuit. Okay, which would explain why the current tends to go up if I keep adding more branches. Oops, I don't know, it's not wanting to write. If I keep adding more branches, now I'm going to have current 3. So the total current at that junction is going to get higher and higher and higher the more branches I put in. And like I described above, each individual branch is like a separate circuit. So if this was a, let's just change the color, if this was a 9-volt battery over here, okay, and if I put a voltmeter across that, it would read 9 volts. And so would this one, 9 volts and 9 volts, because each individual circuit is separate. They're operating off the same battery. So that would be 9 volts across that and 9 volts across that. That's an important factor to understand. All right, so after understanding how Kirchhoff's loops work, if I calculated the current for each individual mini circuit, I just add them up and I'd be able to tell you what the total current in a circuit is. Okay, another way of calculating the total current, well, I'll just describe method 1, which is what I just showed. Okay, if I have a 9-volt battery, okay, and I have a resistor here with a voltmeter attached, and I have another resistor here with a voltmeter attached, and I have another resistor here with a voltmeter attached. Okay, so I have 3 different loops over here. Well, each resistor would have a total of 9 volts going across it. Okay, and let's say each of these resistors is 3 ohms. Okay, and if I wanted to calculate the current going through that ammeter, I would need to find the current in loop 1, the current in loop 2, and the current in loop 3. Okay, and I would have to add them up because the Kirchhoff's loops law, the I total is equal to current 1 plus current 2 plus current 3. Okay, so how do I calculate the current? Well, I'd use Ohm's law, V equals IR. So the voltage divided by the resistance is equal to the current in each loop. Okay, and so I'm going to erase that for a second. So I total is going to be equal to 9 volts divided by 3 ohms for loop 1. That's for 1. Plus 9 volts over 3 ohms for loop 2. Okay, loop 2. Plus 9 volts over 3 ohms for loop 3. Okay, and what would my total current be? Well, the total current is going to be 3 amperes plus 3 amperes plus 3 amperes. The total current is equal to 9 amperes. Well, that's one way of doing it, where I just actually calculate the current in each branch, but that can become quite cumbersome if I have a lot of branches. That's going to take a long time to set that up. Okay, another way of doing it, now notice kind of what's happening here. This is 1 over R, 1 over R, 1 over R, like the R is always on the bottom. So the total resistance, the total current is going to be the total voltage divided by the total resistance. And for some reason, the total resistance is 1 over R plus 1 over R plus 1 over R. So noticing that in here, okay, 9 volts divided by R, okay, 1 over R plus 1 over R plus 1 over R is my R total. We can come up with a relationship that your total resistance in that circuit is 1 over R total is equal to 1 over R1, okay, which would be the first resistor in that circuit, plus 1 over R2 plus 1 over R3. Okay, so this is a formula to calculate the total resistance in a parallel circuit. All right, so here I have a circuit, 9 volts, 6 ohms, 6 ohms, 6 ohms, 3 different branches. Okay, and if I wanted to calculate the total current, I could have calculated the current going through that branch, the current going through that branch, the current going through that branch, and added them up. Or I can calculate the total resistance, and once I got the total resistance, I can then apply Ohm's law, where the total voltage divided by the total resistance is equal to the total current. Okay, so this will help me just calculate the total resistance pretty easily. So 1 over 6 ohms plus 1 over 6 ohms plus 1 over 6 ohms is going to be equal to 3 over 6. Then if I inverse this side, I inverse that. So my R total is going to be equal to 6 over 3, which is equal to 2 ohms. Now that I have that sorted out, I can calculate my total current by saying 9 volts divided by 2 ohms is equal to 4.5 amperes. Okay, so the total current in here is 4.5 amperes. Let's see if that's correct. Okay, 9 volts divided by 6 ohms would give me 1.5 amperes for that branch. For this branch, it's going to be 1.5 amperes. And for that branch, it's going to be 1.5 amperes. Okay, if I add all this up, 1.5 plus 1.5 plus 1.5, that gives me 4.5 amperes using Kirchhoff's junction rule. Okay, so the last thing is, how would I calculate the power in each branch? Well, these are the formulas for power. As long as I know the current going through each branch, and I know the voltage, current times voltage would give me the power. Okay, so 1.5 amps times 9 would tell me the power going through each individual branch. Okay, and if I wanted to find the total power, then it would be the voltage times the total current would give me the total power in that complete circuit. Okay, vice versa, if I knew the current in each branch and I knew the resistance, I could then find the power. If I knew the voltage, which you do, each of these branches has 9 volts. Okay, so 9 squared divided by that resistance would tell me the power in each branch. Okay, and that's that.